I welcome you again to this 9th lecture on mechanical and electrical systems of mining machines. So, this 9th lecture is again a part of module 1, that is the fundamentals of mechanical systems in mining machines. So, we go through the concepts that would be covered in this topic. So, first we will be talking about the types of gear trains. Then we will be going in depth of the types of gear trains, that is simple gear train, compound gear train, riveted gear train and epicyclic gear train. Well, in last class we have discussed about the toothed wheels or toothed gears. So, what did we understand in last class? That when there are two gears or friction wheels are attached to each other, and when we have to transmit power from one shaft to the other, the power can only be transmitted when the friction between these two friction wheels is sufficient enough. However, when the friction is lost, then there will be slippage in between the friction wheels. So, for that there should be tooth or protrusion around these friction wheels, which we call it as the toothed wheels, which you can see is in the form of gears, helps us in power transmission. Well, in last class we understood how the power get transmitted from one shaft to the other and what are the different types of gears based on their shaft position and the gearing type and also on the shape of the teeth. However, in today's class we will specifically talk about if there are multiple gears, like more than two gears if we have, so what kind of gear train we would be talking about. So, in this picture, if you see, this is the first picture which tells that there are only two gears and the teeth are also straight here. Well, in this configuration we see that the shaft is perpendicular to each other and we call this configuration as bevel gear. However, in this kind of configuration where the shafts are not parallel to each other and even not intersecting, we call them the spiral gear. So, one of the classical example of this spiral gear is the worm wheel and worm gear. Now, what kind of gear trains we would be using? When we have only two gears, we call it as a simple gear train. When two gears are meshed with each other, which helps us in transmission of power, we call it as a simple gear train. And what kind of gear train is required? It depends on the velocity ratio that we want to achieve. So, what do we understand by velocity ratio? It is the speed of the driven to the speed of the driver, which is related to the teeth of the driver by teeth of the driven. Well, we understood how a simple gear train looks like. However, it is not the only gear train that helps us in power transmission. There are four types of gear trains. The first one is a simple gear train, when there are only two gears which are meshed with each other and helps us in transmission of power. The second is a compound gear train, where the transmission of power happens when multiple gears are engaged with each other. So, this is an example of a compound gear train where you can see on a shaft there are two gears which are housed over one shaft, and then here you can see there is one gear which is in mesh with this gear. Again, this is the bigger gear which will be again meshed with another gear which helps us in transmission of power from one shaft to the multiple shafts. It is not necessarily that when there are only two shafts involved then only it is called as a compound gear train. Let us say there are multiple shafts and the power has to be transmitted, and on one shaft there are multiple gears which are housed. We call it as a compound gear train. Well, the third kind is the reverted gear train. In the reverted gear train, we have a configuration somewhat like this, where you can see this is one gear, the green one is one gear, the yellow one is the another gear. In this picture, you might be assuming that the shaft is it is only one shaft. However, the shaft of these two gears, they are coaxial. They are not joined in between. There is no joint in between these two gears. You can see here. So let's say this green one is moving at certain velocity, which you can see with this lever that is attached to this gear is moving slowly. Now this is in mesh with this purple one. Now the purple one and this dark green one is housed over the another shaft which is in pink in color. Now this green gear is in mesh with the yellow gear. Now you can see the speed of this yellow gear is more than the speed of this green one. Here you can see when there is a compound gear and there are two gears which is housed on a single shaft, the speed of this smaller gear is equal to the speed of this larger gear because they are housed on a single shaft which has a single velocity. However, here you can see the green one is rotating slowly and the yellow one is rotating at a higher speed. So that is how we know that these two gears, they are not housed on a single shaft but on coaxial shafts. Now there is a fourth kind that we call it as a epicyclic gear train. In epicyclic gear train, you can see that there are two gears which are in mesh with each other. So this is one of the simplest epicyclic gear train where these two gears are not only meshed with each other but they are also connected by an arm here which is denoted by yellow color that you can see in the picture. So here one shaft is fixed, however the other shaft is not fixed and the other gear is revolving around this smaller gear and it is attached to this shaft or this configuration through this arm. Now when we talk about a simple gear train, as we have understood it in last class, there is a driver and then there is a driven. So when the driver is rotating anti-clockwise, the driven is rotating in clockwise direction since they are directly meshed with each other, which may not be the case when we have a open belt drive where the driver and driven, they would be rotating in the same direction. However, when we have a driver and driven meshed with gear, the power transmission would happen in the opposite direction. That is, the shaft A would be rotating, if the shaft A is rotating in anti-clockwise direction, the shaft B would be rotating in clockwise direction. So that gives us the speed ratio of this kind of gear train where we have N1 which is the speed of the gear 1 and N2 is the speed of the gear 2. So that is the driven. This is equal to the reciprocal of their teeth, corresponding teeth. So that is N1 by N2 is equal to T2 by T1. Again, when we talk about another term which we call it as a train value, the train value is the reciprocal of the speed ratio. So 1 by speed ratio is the train value of a gear train. Now when we understand that there is a driver and then there is a driven with only two gears which are in mesh with each other and transmitting power from one shaft to the other, we understand that the driver would be rotating in clockwise direction, then the driven would be rotating in anti-clockwise direction. However, it is our requirement that the driver and the driven should be rotating in the same direction. Then in that case, what we should do? We should have a intermediate gear which would be helping us in transmitting the power from driver to driven. So when the driver is in mesh with the intermediate gear, that is gear number 2, so the direction of the driver and the intermediate gear will be in the opposite direction. However, when we talk about the intermediate gear and the driven gear, now the intermediate gear is in opposite direction of the driver, that is in anti-clockwise direction. So the driven will now move in the clockwise direction. So this mechanism that we are learning here in form of gear train will be very much useful while we are understanding the power transmission in heavy machineries. Well, coming to the third configuration, that is when the driver is rotating in clockwise direction and we have two intermediate gears, that is gear 2 and gear 3. So in this configuration, gear 1 is rotating in clockwise direction, so our intermediate gear 2, that is our first intermediate gear, would be rotating in anti-clockwise direction, which is again meshed with the second intermediate gear, that is gear number 3. The now gear 3 is rotating in clockwise direction, which is meshed with the driven gear. So my gear 4 will be rotating in anti-clockwise direction. Now when such configurations are used, when the distance between the driver and the driven is more, we use such configuration. So all of this kind of configuration, even though there are two gears or multiple gears, this kind of gear trains we call it as a simple gear train. So what is the difference between a simple gear train and a compound gear train? When on one shaft there are multiple gears are housed for the power transmission, we call it as a compound gear train. While when there is only one gear which is housed on the shaft from where the power transmission takes place, we call it as a simple gear train, as we have discussed herein. Now when the distance between the driver and the driven is more, so we use this kind of configuration, and this kind of configuration we may use when we want the driver and driven to rotate in the same direction. So the third configuration can also be used when there is also a limitation of the size of the gears that are being used. Well, for such simple gear train, let us see about the configuration 2. So how do we get the speed ratio? So, well, we understand that my N1 by N2 will be equal to T2 by T1, and my N2 by N3 will be equal to T3 by T2. Now I multiply the LHS of N1 by N2 with the LHS of N2 by N3. So here my N2 gets cancelled, and here when I multiply the RHS of these two equations, so my T2 will get cancelled. So finally my N1 by N3 is equal to T3 by T1. So what does this says? That there is no effect of the intermediate gear on the speed ratio between the driver and the driven. So my driver is N1 and my driven is N3. So my speed ratio will be N1 by N3 is equal to T3 by T1, as has been shown herein. This is for simple gear train configuration. Now when we talk about the train value, it is the reciprocal of the speed ratio, which is given by the speed of the driven by the speed of the driver, which is equal to teeth on the driver by the number of teeths on the driven. Well, there are certain things that we need to understand. The intermediate gears here are called as the idle gears, as it does not have any effect on the speed ratio. And when do we use this kind of idle gears? when we have to connect two gears which are at a larger distance from each other, or else we have to obtain a desired direction of the driven gears, as has been explained in the previous slide. Well, now coming to compound gear trains. So this picture shows you a classical example of how the compound gear trains look like. So you can see here there is a driver which is housed on this shaft A. Then there is gear 2 and gear 3 which are housed on the shaft B, gear 2 and gear 3. Now gear 3 is meshed with gear 4 which is housed on shaft C, and on shaft C there is gear 5 which is now enmeshed with gear 6 which is housed on shaft D. So what we are seeing here, from shaft A the power is getting transmitted to shaft D. However, there are multiple intermediate gears which helps us in power transmission. Well, we can see that the speed of gear 2 and gear 3, they will be same and also in the same direction. So let's say my gear A is rotating in clockwise direction, my gear 2 and gear 3 both will be rotating in anti-clockwise direction. So gear 1 and gear 2, they are meshed with each other, so that gives a opposite direction, and gear 3 is housed on the same shaft, so that is why it will have also the same direction as gear 2. Now my gear 3 is having anti-clockwise direction and gear 4 is having clockwise direction, as gear 3 and gear 4 are meshed with each other. Now since gear 4 and gear 5 are on the same shaft, so they will have the same speed, and gear 5 and gear 6 will be having different rotation, that is gear 5 is in clockwise direction and driven gear is in anti-clockwise direction. Well, how do we find again the speed ratio? So from gear 1 we can go till gear 6. So N1 by N2 is equal to T2 by T1. Now my gear 2 and gear 3, they have the same speed, so but they are not meshed with each other. So my N3 by N4 will be equal to T4 by T3. So as you can see herein, so the first N1 and N2 gives us N1 by N2 is equal to T2 by T1, and then 3 and 4 gives N3 by N4 is equal to T4 by T3. Then we have gear number 5 and 6, where my N5 by N6 will be equal to T6 by T5. Now we multiply the LHS, equating it with the multiplication of the RHS. So what do we get? So my N1 by N2 multiplied with N3 by N4 multiplied by N5 by N6 gives me T1 by T2 multiplied by T4 by T3 multiplied by T6 by T5. Now we understand the number of teeths on this individual gear are not same, they are different. So, well, but how about the speed? Since N2 and N3, they are housed on this shaft B, so their speed is same. So this gets cancelled out. Now my N4 and N5, they are also housed on the same shaft. So my N4 and N5 also get cancelled out because they are equal. So finally my equation boils down to N1 by N6 is equal to T2 multiplied with T4 multiplied with T6 divided by T1 multiplied with T3 multiplied with T5. So one thing you may notice here, T2, T4 and T6, T2, T4 and T6, they are the driven gears, and T1, T3 and T5, they are the driver gears. So ultimately, what do we say the speed ratio? It is the speed of the first driver by the speed of the last driven is equal to the product of the number of teeths on the driven by the product of number of teeths on the drivers. Now when we talk about train value, it is reciprocal of the speed ratio and the equation is given herein. Well, when do we use a compound gear train? When we need a very large speed reduction from the first shaft to the last shaft, and when the gear, that is the final gear on the driven shaft, is very small, we use a compound gear train for smooth transmission of the power from one shaft to the other. Well, if we have to, instead of a compound gear train, we have to use a simple gear train, then there will be a large speed reduction. So the last gear, let's say the driver gear is a very small one, and then we have to reduce it substantially to the driven gear. So the last gear has to be very large. And what is the allowable limit of this transmission? It should not be in excess of 7:1. So that is why there are multiple gears which are employed in between, so that the speed reduction can happen smoothly. Now coming to the design of spur gears. Well, we understand the distance between one shaft to the other, it is constant, it does not change. The shafts are fixed, unlike in the epicyclic gear train where one shaft is fixed, the other is not. When we talk about a simple gear train or a compound gear train or even in a reverted gear train, the distance between the shaft is fixed. So how do we quantify this distance? Let us say we tell it as x, and then how do we write it? It is, let's say this gear has a radius of r1 and the other gear has a radius of r2, which we can tell it as d1 plus d2 by 2. So this is the distance between the two shafts on which there are two gears which are meshed with each other. Now we also know that when the two gears, they have to mesh with each other, the module of these two gears has to be same. That is d1 by t1 should be equal to d2 by t2, or else these two gears will not mesh with each other. So my n1 by n2 is equal to T2 by T1, that we know. So there directly we can write it as D2 by D1. This gives us a relation of speed ratio not only with respect to the number of teeths but also with respect to the diameters of these gears. Well, now coming to the reverted gear train, as I was trying to explain you of how does this configuration looks like, you can see here a configuration which tells how a reverted gear trains look like. So here you can see there is one gear here, which is gear 1, which is in mesh with gear 2. You can see in this configuration where there is one shaft and on it you have gear 1, and then there is another shaft on which you have gear 2. On the same shaft you have gear 3. You can see this is a compound gear where on the same shaft you have another gear, that is 3. So here my N2 is equal to N3. Now my N3 is meshed with N4. So however, these two shafts are coaxial, that is the center distance here is equal to the center distance here. However, these two shafts are not connected. So how the transmission of power can happen? So from gear 1, let's say it is meshed with gear 2. So gear 1 is rotating in anti-clockwise direction. So gear 2 will be rotating in anti-clockwise direction. Now my gear 2 is rotating in anti-clockwise direction, and on the same shaft we have gear 3 which will also rotate in anti-clockwise direction. Now it is in mesh with gear 4. So which will be rotating now in clockwise direction. So the direction of gear 1 and gear 4 will be same, but their speed will not be same. So my N1 will not be equal to N4. That is the condition of a reverted gear train. Well, how do we find the speed ratio of a reverted gear train? So what we know that we can directly write N1 by N2 is equal to T2 by T1. Now my N3 is in mesh with N4, so N3 by N4 is equal to T4 by T3. So what do I have to find? I have to find what is the ratio of my N1 by N4, which I can directly write it as T2 by T1 multiplied by T4 by T3. It is same as the compound gear train. So as you can see here, so if I multiply N1 by N2 multiplied with N3 by N4, my N2 is equal to N3. So it gets cancelled out and we get N1 by N4 is equal to T2 multiplied with T4 by T1 multiplied with T3. So this again gives us a relation that speed ratio is the product of number of teeths on the driven by the product of number of teeths on the driver. Well, there is also another relation that we may see here, that is the center distance. Since the center distance is same, so here my x is equal to R1 plus R2. Now here again we have the same x which is equal to R3 plus R4. So you can find this relation R1 plus R2 is equal to R3 plus R4. Now let us assume that the module of all of these gears are same, that is M1 is equal to M2 is equal to M3 is equal to M4. So directly I can write this relation as M T1 plus M T2 is equal to M T3 plus M T4. Now when I cut M from both the sides, I get a relation of T1 plus T2 is equal to T3 plus T4, which is a relation that we obtain in reverted gear trains. Now coming to epicyclic gear train. So in epicyclic gear train, what do we understand? That my gear A is housed on a fixed shaft. However, my gear B is revolving around my gear A with an attachment through arm C. My gear, the shaft on which my gear B is housed is not fixed. So now in such scenario, how do we find the speed ratio? Because one gear is not fixed onto a shaft. We can directly find when these two gears are in mesh. However, if there is a complicated problem when there are compound gears with epicyclic gear train, then how would we find the velocity ratio or the speed ratio? Let us first try to solve this problem with respect to a simple epicyclic gear train as is shown in this picture. Well, there are two methods. One is a tabular method and another is the algebraic method. In tabular method, so let us do a table something like this, where we have TA as the number of teeths on gear A and TB as the number of teeths on gear B. So we will go in multiple steps, and we have the condition of motions, and then we will be revolving each element. So here we have three elements. We have arm C, we have gear A, and we have gear B. So here first what we do is we take the arm as fixed. So that is, the arm does not have any kind of revolution with respect to NA or NB. So we take it as 0, and our gear A rotates by +1 revolution, and that is anti-clockwise. Now when we talk about simple gear train or compound gear train, there is no directional component. However, in epicyclic gear train there is a directional component. So when we are taking anti-clockwise, we are taking it as positive, and when we are taking clockwise rotation or revolution, we are taking it as negative. So here the first condition is, while the gear A rotates in anti-clockwise direction and it makes +1 revolution, the gear A makes +1 revolution, how much my gear B would be making? That is, my NA by NB will be equal to TB by TA. My NA is rotating in clockwise direction, that is +1, but my NB is rotating in anti-clockwise direction. NA is rotating anti-clockwise, NB is rotating in clockwise direction. So it will be -NB. So this gives me the relation of TB by TA, which gives us NB will be equal to -TA by TB. So which is written herein. Now the same thing we do where my arm is fixed and my gear A is given +X revolution. So my gear B will be having -X TA by TV times of the revolution. Now we add +Y component to C, A and B, and then we add all these motions. So when we add this column, it gives us +Y. When we add this column, we just take this variable components. So then we have X plus Y, and in gear B we have Y minus X TA TB. So if we get to know what is Y or what is X, we will be able to solve the speed of arm C, gear A and gear B. Now the same thing, let us look from algebraic point of view. Let us say my arm C is fixed in this epicyclic gear train. So what would be the speed of my A with relative to C? It will be NA minus NC. And what would be the speed of gear B with relative to C? This is NB minus NC. So now since gear A and gear B are directly meshed with each other and they will be revolving in opposite direction, so here my equation of speed ratio, that is NB minus NC by NA minus NC, will be equal to minus TA by TB. Here we have the directional component. Well, in this equation, when my arm is fixed, that is the speed of NC is 0. So my equation boils down to NB by NA is equal to minus TA by TB. However, let's say in this equation my gear A is fixed. So how my equation will be? It will be as NB minus NC by minus 0 minus NC, which is equal to minus TA by TB. So here my final equation will be something like NB by NC is equal to 1 plus TA by TB. And if we have we know the speed of NC or NB, we will be able to find out the relation of the speed of the individual elements in a epicyclic gear train. So more about how to solve this problem we will be going through while we solve in the tutorials. So this is the reference that we would be following for this chapter, that is Khurmi and Gupta theory of machines. Thank you.